Okay, so we're going to look at further horizontal motion questions. This time we're going to look at where it's not on a flat surface where the center is on that flat surface, or indeed if it's in the air, but the whole idea where you've got that sort of the motion swinging around in a horizontal circle. Everything is in that horizontal plane. What we're going to now look at is a more sort of conical situation where the center of the or the end of the string, for sake of argument, is above that plane that contains the circular motion. So here you can see there's a point here at the top here, and this is the top of the string, the end of the string with a weight on it, and the weight is making at circular motion around. Now we can see I've highlighted that you've got the height above that horizontal plane, at which point the string ends at. You've got the length of the string, okay, and you've got the radius of the circular motion. And obviously it's a right angle triangle, so if you know 2, you can work out the third using Pythagoras. That's the first thing to say. Now, in terms of the forces that are acting on this, you've got the tension. So the tension occurs in that string, and that effectively is what's creating that centripetal force. But you have to appreciate that there are 2 components to that. I'll split that down. You've got a vertical component and a horizontal component. Now, you may get told something about the angle. You could work out the angle using trigonometry if you know certain measurements of that right angle triangle. And whatever that tension along that string, we need to appreciate that we've got t cos theta, and horizontally we've got t sine theta. Okay, and we can break that force into 2 separate parts. There is another force that's at play here, and that is the weight of the object, and we can appreciate that there is going to be its mass times by gravity vertically down. So one of the key ideas to need to use is the fact that the force is vertically, so that the mass and gravity causing a weight vertically down, and then the vertical component of the tension that's at an angle, so t cos theta must equal mg in order for us to be able to have this circular motion where you've got that horizontal circular motion. So put simply, the force going up must equal the force going down if that is going to be that horizontal circular motion. So that's an important rule to appreciate. So as I said to you, in this current situation, if this is a pendulum style conical movement and it's freely hanging, then you have t cos theta is equal to mg. Now, just as an aside here, if you have the mass, the body acting against something, so we will look at if it's inside a sphere, but also where the body might be sort of in a horizontal motion, but it's lying on a flat surface like a table, for sake of argument, then you're going to have the normal reaction. So if the movement of the object is moving around horizontal circular motion, but it's on a table effectively, and the table is helping to support its movements, you're going to get, in addition to t cos theta, you've also got effectively a normal reaction. Okay, if it's in a cone, a cylinder, in a sphere, then you're going to get a normal reaction that's going in a direction that is towards the center of the sphere, and we'll look at that scenario as well. So from that sheet of questions that I gave to you in the last lesson, question 11, a conical pendulum consists of a particle mass 5 kg attached to a light string of length 1 meter to a fixed point at P. A particle describes a horizontal circle of radius r with the center of the circle being vertically below P. The string makes an angle of 30 degrees with the vertical. Okay, so that angle it's referring to is that angle in there with the vertical. So find r, find the tension in the string, and then the angular velocity of the particle. So we're going to find the angle. We have to find the tension that's in that string, and then what speed is it going around in that circular motion. So looking at that right angle with the angle of 30 degrees, the hypotenuse of 1, we end up with that opposite being 1 sine 30, which works out as a half, 0.5. So that's the radius. Now if we draw, just appreciate and draw the forces that are acting. We have tension going at that angle of 30 degrees. We've got the object with a mass of 5, so the mass going down is 5g. The tension has two components to it. It has a vertical component and a horizontal component. The vertical is going to be that tension multiplied by the cos of theta, so tension cos 30. The horizontal component, which effectively is creating the centripetal force, is tension multiplied by sine theta. So that's T sine 30. And the first thing we can do is we can say, well, vertically, your 5g has to equal the T cos 30. So let's just write that out. So vertically, we have 5g is equal to T cos 30. Now cos 30, well, if we just do 5g divided by cos 30 straight away, this calculation, we end up with 56.58. Okay, so we know what T is. So once we now know what T is, we can work on this horizontally. We can talk about the force that's acting in towards the center of the circular motion. So if we appreciate that force moving in is the T sine theta, so using F equals m r omega squared, we have the tension multiplied by sine 30 must equal the mass times by the radius times by omega squared. Well, T sine theta, that's going to be 56.58 multiplied by a half. So we end up with omega squared being equal to, when you bang it out in your calculator, we end up with 98 root 3 over 15. And therefore W equals 3.36 radians per second. So just to recap that, so we start off by looking at the vertical forces in play. They had to equal to each other, so the force vertically had to equal to 5g, so we were able to get the tension as a result in newtons. And then horizontally, we looked at the fact that this horizontal component of the tension was the centripetal force. So we can use F equals mr omega squared and insert everything we have. And then as a result, we were able to get omega, the angular velocity.